video, I again look at another method of redistributing weights, basically data compression only. Now again, our objective is to map a number which is less than m equal to 2 power L dash to a value which is less than s equal to 2 power L, where L dash is much larger than L, right? So our objective is to perform this mapping. We group we consider the M is the information to be coded, S is the code corresponding to the information, right? Now we know if you take a general conventional binary number, if the weights are W0, W1 and so on up to the ith bit is the W1 and so on, like this, right? If we consider only the L bits of S, we will have WL minus 1. Now the invariant property that must always be maintained is Wi plus 1 is equal to 2 times Wi, right? This property must be maintained for the, it will actually come out to 2Wi plus 1, that's okay, we can, but we are largely interested in this, slightly more than 2 times Wi. Now Wi can always be a proper fraction, in which case you can do that. So our objective is this. Now what we try to do here is, we try always to maintain the distribution of the weights among the bits of S while trying to maintain this necessary invariant. Now what we try to do is, if you first group the L dash bits of M into n bits each, we assume a base B equal to 2 power n, right? So we group the L dash bits of information into n bits each. So let L double dash equal to L dash by n. Now this method of coding is based on, so essentially M is equal to B power L double dash. This method of redistributing weights is based on the assumption that if D is any digit 0 less than or equal to D less than equal to B minus 1, right? If we consider the expression D power at L double dash, what happens here is, as the value of D decreases, right, the value corresponding to D power L double dash also decreases. Finally it comes to 0, but the next one will be 1. 1 power L double dash is 1 only, right? So based on the observation, is it possible to decrease the values of digits D in such a fashion that we always maintain the invariant condition also? Now of the couple of approaches that I adopted, this one seems to be promising, and it appears as though that it might in fact be possible to do such a thing, close to possible, and that it might be possible to maintain the invariant. So now objective is, so to that end we would like to maintain the invariant. Now as we are interested in that, so Wi must be equal to W. I'm assuming that D decreases from B minus 1 onwards. Wi plus 1 by 2. This is the invariant I'm interested in maintaining. So we try to determine a value x such that D minus x whole power L double dash is equal to D power L double dash by 2, which gives you x equal to D minus x equal to D by 2 power 1 by L double dash, taking the one L double dash as the root of this, right? Or x is equal to D times 2 over 1 by L double dash minus 1 by 2 power 1 by L double dash. Okay, now this factor is always constant, right? If we take right? So this factor is always constant. Let C is equal to reciprocal of this. By 2 power 1 by L double dash minus 1, right? So essentially D varies as D minus X only, which will be D minus D by C, right? Which will be D times C minus 1 by C. Right? Okay, so that will be this thing. Now what happens if you do d minus x minus d minus x by c? What happens is it will become d times c minus 1 by c the whole square. In general, the value of d decreases as d times from b minus 1 into c minus 1 by c times whole power j, some integer j. That is, you're starting off with b minus 1, right? Now if we adopt the convention for the weights, we are interested in the value of d as it decreases. So we have w weights, the value of I varies from 0 up to L minus 1. We want to know the value of L minus 1. It will be close to b, but will not be exactly b. Right? So it basically varies as b minus 1 into the value of d varies as b minus 1 into c minus 1 by c, corresponding to the weights which are basically d power L double dash for all of this, di power L, c minus 1 by c whole power L minus 1 minus I, where for the ith weight. Okay, L minus 1, this is where 0 less than equal to, so d is essentially as follows. Where 0 less than or equal to I less than or equal to L minus 1, right? What are the corresponding weights for each value of I, di? Wi will be nothing but di, d naught, d1, d2 and so on. So Wi is nothing but di whole power L W dash, right? So these are the L weights that you must assign to as you can see. What should the value of L itself be, right? For that we need to determine the value of the base B itself such that B, instead of B minus 1, I will assume B here, roughly B times C minus 1 by C whole power 1 by B minus 1 is equal to 1. We can assume here B minus 1 times which should give you b minus 1 whole power 1 by b minus 1 is equal to c by c minus 1. Which gives you the value of L is equal to b minus 1 times b minus 1 by L dash, not L double dash, but L dash. So this is the value of L. So for a given L double dash, we can reasonably try to determine L. L should not be too small, and then distribute the weights as I just determined right now. Then you should get decent compression. And the number of iterations required for it will be very, very few or very, very small. I'll just repeat it again. We need to determine B such that B minus 1 times C minus 1 by C whole power 1 by B minus 1 is equal to 1. Which will give you roughly the value of L is equal to B minus 1, performing all the substitutions, whole power B minus 1 by L dash, not L double dash. Okay, so this is what the value of L will be. L need not be too small. L can be slightly large. For I am talking about large number of bits, like something like 512 MB or something in 512 bits or 1024 bits, something like that. L can be so many bits. The weights will satisfy this property. Then you can determine a value of B which satisfies that, and then code such a large value in by assigning weights in this fashion as we determined above previously. So then if you code the information in those number of bits, it will still maintain the order also, and at the same time in the fewer number of bits it will be able to code a very large number of information. The amount of repetitions required will be very, very small.